Alright, hello everyone. I am Professor Caudill. Alright, so before we get into the problem sets, figured we would just kind of take a step back and, what is the AI2C? What is it about? So we're all kind of used to, having the gun to our heads of thermonuclear destruction. And that gun to our heads is only going to get more noticeable as there's more drones in the air. Um, so I feel like in the future, the sky will be filled by objects that can easily kill us. So, AI2C trying to automate all labor, or, and this is like a realist class. This is like step one, like trying to automate anything. Step one, know the physical reality, know how many actions you're doing so you can try to build a system that does that action. Like if you're doing, you do 3 actions per task. Okay. Automation is, so like the definition I like to use of automation is that means machine does it in one action. So if you have n actions, automation is n to 1. So that means human to machine. That is essentially automation to me. You're converting human action, convert human actions into machine actions. And you might be wondering what's machine, what's a human? Again, these terms they're blending into each other. It's hard to differentiate. It's 30 definitions of consciousness, intelligence. So people that express their individuality can't really define what they mean by individuality when pressed. That's from my observation. But so machine actions, if you just remove the ontology, if you remove all ontology, automation is essentially this. You're taking in actions and you're converting it to one, let's say in -1 actions. Okay. So I know I asked a language model about this once. What concepts in physics um, describe things like this? And it did give me an interesting answer. Let's see if it can bring it up. I remember asking it something like, what is the concept in physics that describes converting a series of n actions to a system that can do n-1 actions to do the same task in minus one action. Efficiency or optimization, least action, principal stationary action. Least action is a path taken by a system between 2 points in space for which the action is minimized or stationary. So stationary is key. So if you've done any linear algebra, you've seen Markov change where you have a bunch of numbers. And you do some processing on it to where you find like the underlying symmetry. So this is, you would find some stable state of a matrix given some unstable state, and you find that stability over time. So I can show you. Give me an example of this using Markov chains. So Markov chains are stochastic models. What is stochastic? I think that means it's changing. Let's focus on that keyword real quick. Stochastic models, it's a random process, probability sequence, how often things happen in a moment. So possible events. So there's probability Markov. So it's like, what's the probability that you do in actions? So instead of walking, person uses a bike to reach it more quickly. Taking the bus. So it's not, it's like if you're saying walking, so if it's like if time could be an action, time is like your action, and you're doing it in less time. I guess it depends on how you look at it. Yeah, ultimately, there's always going to be threats to our life. Even like if we digitize or informationalize the mind, there's still the heat death, quote, the heat death or big crunch, where the universe expands so thin that all the heat is basically unusable. So I don't know if I believe that, because if you're following the thermodynamic law, where it's like energy can't be created or destroyed, then if energy goes into a state that's inaccessible, that's essentially destroyed. It's as if energy went into a black hole. It's excessive. If it's inaccessible to us, it's no different than being created. It's no different than being destroyed. So I don't know. Maybe that thermodynamic theory needs to be revised, or maybe the big crunch, um, big crunch, all those theories, they might just need revised. So one or other of the astrophysics or thermodynamics, I think one of those needs to be revised. But either way, to here now, our lives are threatened by drones and nuclear, chemical, the seaborne weapons. So top priority should be just transcending the biological human body, digitizing the mind. So if this physical body gets destroyed, then it's not the end of the world for me. I can upload into another body, another physical substrate. So, you might be wondering how that might be automation. So if you're taking one neuron, if you can do the task of one neuron, if you can do the task of 3 neurons with 1 neuron, then that's automation. Uh, we know how fast. We know that artificial or just computer networking in general is faster. They send information faster through a copper wire than it takes to send it down your spinal column. Like I think a neuron travels down the brain at 1/300,000th the speed of light. So that's how fast a neuron travels. Travels down the spine where, just any electrical thing just goes at the speed of light minus resistance. So C minus resistance equals artificial neuron and computer speeds. And because it travels faster and it's simple, more simple, but captures the same information. It can be transferred to, like a data center in a satellite, just in several satellites. So it's just harder to kill us. That's really what it comes down to, is just extending life, defending life, uh, the big pursuits of the human endeavor. So let's get into the problems. Position, displacement, average velocity. Direct x-axis is directed upward vertically. Okay. It's kind of a weird phrasing. Why not just say y? But all right, so position of a particle is 5. So our initial position is 5. Okay, so it's 5 plus x. Let me rephrase that. Let's say this is x naught. This is x. So part A is answered by saying x naught plus 5 equals x. And likewise, okay. So let's move on to 25. car is going 2 kilometers west. I was going this way, 2 kilometers negative I. Kilometers west of a traffic light. Okay, so the car is here. I'm thinking that's what it's saying. The car is here. The traffic light is here. So I'm guessing the car is approaching the traffic light. And this is your T, not. And then at T final is 6 minutes. 0 at T is 6. It's 5 kilometers. I hat. So this is the origin. Okay. What are the car's position vectors at these 2 times? So, I think I already wrote it. This is a position vector, v1, and this is v2. What's this displacement? Between 0 and 6 minutes. So we're going to take 5 minus 2 is 3 kilometers. So you got displacement. I think of it like, what's the, if we're traveling within a radius, within a circle, the displacement is whatever that diameter is. So in that case, it would be plus absolute value. So that'd be 7 kilometers. Okay, 26. Shanghai maglev trains connect Longyang Road to Podang International Airport. A distance of 30 kilometers. So we have T naught in 8 minutes. Average velocity. So should have this memorized by now. It is v minus v naught over 2. So that's 30 minus 0 over 2 is 15 meters. No. Velocity is meters per second, right? So how are we factoring in this? Is it this T0 minus, is it T final minus T0? 30 over 8 kilometers a second, so that is about 4 kilometers a second. 8, 16, 24, 32. Where I'm getting that from. So average velocity. B 30, B naught 0, B naught 0. T is 8. What's the average velocity? And show the abstract equation used before plugging in. Okay, so I was right the first time. This is going to be 15 kilometers a second. Why would the denominator not be final time? Oh, why is it giving me different answers? Now it's saying this is right. This is the worst. Okay. Physics, average velocity. Average velocity is how do you find it? Initial velocity? How do you find final? How do you find okay. So maybe it's simplified. So average velocity can be v or if v times time, which is 8, v t v times t1 plus v over summing all the t's, so that's gonna be 8 30 plus 0 0 over 8. So, man, why am I getting different average velocity functions? The actual book we're using, by the way. Okay, this is doing t minus that, so that's what I got 4 kilometers a second average velocity the first time. It's like, why is it like that? Maybe the book says velocity is a vector sorry. V is a vector. V is a vector. So like, velocity is already has time in it. So if you know your initial time, so like you're describing like he ran 5 meters per second. That's your, let's see, finished the race at 5 meters per second. Start of the race, he started at 3 meters per second. So time is already in the numerator. So 5 minus 3 over 2, 2 equals 1 meter per second. Is that right? Man, this is tough. The position of a particle moving along the x-axis is x is, oh, this is a function, right? Okay. 4 minus 2t meters. So what's time to cross the origin? Find across the origin. So what is that saying? When trying to find when x is 0. So when 0 is 4 minus 2t. So t is 2 seconds. Okay. What is the displacement of the particle between 6 and 3 seconds? Okay, so we're going to do first we need to find the velocity. So velocity is x is -2 meters per second. To -2. At what time does the particle cross origin? Displacement of the particle between that. Okay, so displacement. Displacement. Tempted to do 2 times 2 minus this. I'm tempted to do this, but I don't. I have doubts about this. 3, 4 minus 12 minus 8 minus 4 minus 6. 4 minus 6, -2 plus 2, -6. So absolute value is 6 meters. Should be fine. I mean, we don't need to find velocities. We're just getting asked about the position. So I think it went 6 meters. All right, 28. So he's going 8 kilometers, 20 minutes. Then he turns and head west. Then he rides back. Forty minutes. Final displacement. So total displacement. All right. I know we're gonna have to sum all of the magnitudes. So 8 plus 3.2 plus 16. Okay, so that's going to be his final displacement. What is his average velocity? Okay, so we're going to take 820 plus, I'm generalizing the average velocity function. I'm going to say it's 823 to 8 plus 1640 over 3. I'm using 3 instead of 2 because I think it's, if you have 3, I think this v minus, or v minus v naught over 2, that's just describing 2 vectors. But what if it's 3? Then it's v minus v1 minus v naught 3. I would think. Anyways, so. Alright, so I'm not gonna calculate that. You could do it if you really want to know it. 29 February 15, 2013, a super bolide meteor. '29. Okay, this page break is very weird. Like we're not even on a page break. Just kind of like we're on the same page and should be here, but no, and is, we're just gonna start paragraph here, I guess. So 23.5 kilometers above the earth. What is it? It's a meteor? Yeah, okay. Blast wave took 2-3 minutes to reach. Blast wave traveled 10 degrees above the horizon. Okay, so you have a horizon, you know, like the sun. Sun, so it's coming at you at 10 degrees. So what was the average velocity? So um it's like, is this relevant? Sometimes they just give you irrelevant information that you don't need. All right, so average velocity. So we're gonna do so V naught's going to be 0. It's just going to be 23.5 over 2.5 divided by 2. Right? Yeah. So we're gonna get about 47 divided by 3, so about 15 meters per second. Like I feel like I should not be struggling with these, but I am. Instantaneous velocity, woodchuck runs 20 meters to the right, 5 seconds. What is the average velocity? Average velocity of the woodchuck. So we're gonna do 20 over 5 plus 10 over 3 divided by 2. It's our average velocity. What is its average speed? So speed equals absolute value, whatever that is. Okay, 31. Okay, so this is our graph. So what's the velocity? So we're increasing linearly here. So that means our velocity is constant. So it's going to be constant. And then it's going to drop to here. And it's going to drop even faster. And it's going up. And increasing slowly. And then it increases quickly. I don't know if that's right either. Yeah, I'm not. I hate sketching graphs. I'm sorry, I can't do it. Can't do it. All right, 34. Object has position function x t equals 5 t meters. What is the velocity as a function of time? All right, so x is 5 meters. An instant. I was saying a second, but this is an instant. So you're gonna have, it's gonna be x of t. We know that's a linear function, so derivative is gonna be 5. It's gonna be like that. Okay, 35. A particle moves along the x-axis. What is the instantaneous velocity? Okay, so they want x equals -4 t plus 10 at 2, and 3. So they want, so x at 2. I guess I could say x at 2 is 2 times -8. 2 times 4 is -8. So that's 2 meters. X 3 is -12 plus 10, -2 meters. So the speed is 2 and 2, the absolute value. What is average velocity between, so what's the average velocity? So that's gonna be -2 minus 2 over 2 equals -4. 2 -4 divided by 2 equals -2 meters. Meters an instant. It's like if we're physics, do we make dt is Planck's constant, or do we just write dt equals, the instant time? So it's like, do we use what might be supported in the literature? Do we use, it's like, how much abstract math do we want in our physics? What's better? If you're doing discrete quantities, then all of calculus falls apart. But I guess you could round up. You round up from a differential time to Planck's constant, and maybe not be too bad. So, all right, we got another one. 3t cubed plus 5t time is the velocity equal to 0. So, is 3 times 3 is 9t squared plus 5. 0. We want to know when this is 0. -5 over 9 equals t square root -5 over 9 t. I don't know if we can do square root of negative numbers. Velocity is 9t plus 5. What is the time when it never equals 0? Is this reasonable? No, it's not. It's not reasonable. Okay. 37. cheetah acceleration rest. So v naught equals 0. V is 30 meters per second. Okay. What's its acceleration? Oh, I see. Velocity is 0. Alright, so we're going to use probably one of these kinematic equations, won't we? So we know it's going 30 meters in 7 seconds at rest. So 30 over 7 is its acceleration. Okay. So we're going to do the same thing. 282 meters per second. Wait, for the last problem, this should be divided by 7, right? So shouldn't it be... Wouldn't that be the acceleration? Because v has to be meters per second. Maybe someone viewing this, it's making more sense for you. So 282 meters per second is, so we're doing A, solving for A. So since this is per second or per the smallest unit, what we're just going to do is our acceleration. All right. Okay, so if you wanted to take this, so that's about 60. So divided by 9.8. So we're doing about 6 G's. 6 G's. So that's, if there's anything that you should remember in the video, it's probably that. It's probably you can express accelerations by n G's, you know. It's probably best sketch. So okay, we don't sketch graphs here. It's not necessary. Commuter backs her car out of her garage. T equals question mark. We want V. Okay, so we know A, don't know T, we know V, V naught. So we're doing this solving for T. So we're using equation 3. So we're doing 3. V is 0 is 2. 1.4 T 0. And we're getting, that's about T equals 1.4 seconds. If she brakes to a stop in 8 seconds. Hurting my brain. If she brakes to a stop. You draw a picture. What is her, like, is he asking for the total acceleration now? So they want V. Do they want an updated total acceleration? So it's asking for if you know if it's is it V AT plus V naught. So it's asking for 2. It's 1.4 plus 0.8. So 2.2 A plus V naught. I think that's what it's asking. So we're gonna swap this to A, swap this to 2.2 seconds. So I'm getting 0.9 is her total acceleration over this interval if she includes braking with backing up. I think that's a good place to stop. So next time we'll pick up on 41. 41. All right. Thank you guys for hanging out. It was a pleasure. Yeah, see you next time.